All right, hi guys. This is Chemistry 4, Week 14. This is our first video of the week. So this week there's going to be two videos, and they both cover Chapter 16. Chapter 16 is the first chapter that we're going to do in the biochemistry portion of the course. So let's just get started. Chapter 16, Amino acids and proteins. There are four types of biomolecules that we're going to talk about in this last 1/3 of the course. Chapter 16 covers one of those types of biomolecules. First type of biomolecule is or are proteins. That's this chapter, chapter 16. That's this week. Second one is carbohydrates, and that's covered in chapter 13. Go back a little bit. Lipids is the next one in the progression. That's number 3. That's chapter 15. And lastly, we're going to do our best to try to get to nucleic acids, which will be like the last week of the course, and that's chapter 17. All right. So today we're on number 1. Today's video and the next video, both videos from this week, week 14, will be on number 1, proteins, chapter 16. All right. So let's just get started. Protein structure and function. Proteins. Proteins are polymers of individual amino acids linked together. So amino acids contain both an amino group, and I'll show you what that is in just a second, and they also contain a carboxylic acid group. So an amino group is like little NH2 or NH3 plus. Carboxylic acid group is a C double bond O with a COO with a COH. So on the far left there, that NH2 group, that's my amino group. And on the far right is my carboxylic acid group, C double bond O, OH. Now, what is that R with a box around it? That is called the side group or the R group. And of the 20 essential amino acids, the R group is different for all 20. Okay, so the carbon has an NH2 off to the left. It's got a COOH off to the right. It's got an H above, and then the R group below. At least the way I've drawn it, that's how an amino acid looks. Okay, and I will show you some other ways in the very next video. Amino acids can link together to make proteins. Okay, so what I'm drawing right now is I'm drawing a amino acid that is linked to another amino acid. So this has two amino acids linked together, and they're linked together via a peptide bond. Now, a peptide bond we've actually learned about before, and we learned about it as an amide. So if you see in the middle of this compound here where the C double bond O is attached to an NH, that's a new bond. Okay, so if I have two amino acids linked together by one peptide bond, this is called a dipeptide. Okay, so what have I circled there? Well, I circled the R groups for each one. So the first amino acid is actually valine, and the second amino acid is, I believe that's serine. Cysteine, sorry. Okay, so by the way, before I get moving on the star here, if I had had 3 amino acids linked together, that would be a tripeptide with 2 peptide bonds. You always have one less peptide bond than you do amino acids linked together. Now, each protein has what's known as an amino terminus, something that's nitrogen related, right? And a carboxyl terminus, something that's C double bond O related. All right. Now, the way I draw them, I always make the amino terminus or the N-Terminus on the left, and my carboxyl terminus or my C-Terminus on the right. All right. And we'll do an example below, but if you look at the top one there, you see how I have that NH2 group on the far left? That's my N-Terminus, and then I got the C double bond O, OH. That's my, on the far right, that's my C-Terminus. Okay. So proteins differ in their numbers and types of amino acids, but they all have the same N-Terminus and C-Terminus. So what I've just been talking to you about is something called primary structure. Proteins do have 4 levels of structure. We will focus almost exclusively on primary structure. So let's define primary structure, and then we'll take you through 2, 3, and 4. So proteins have 4 levels of structure. The first structure is primary structure. That's the sequence of amino acids in a protein chain, a peptide chain, polypeptide chain, etc. For example, ALA-PHE-SER. Those are 3-letter abbreviations for certain amino acids. So the first one is alanine, the second one phenylalanine, the third one is serine. So I'm drawing alanine, and then I'm drawing a peptide bond that links it to phenylalanine, and then I'm drawing a second peptide bond, C double bond O N, that links to serine. So if I see ALA-PHE-SER, I've drawn this all out now. 3 amino acids is going to have 2 peptide bonds linking them together. Remember that. The number of peptide bonds you have is always 1 less than the number of amino acids you're making in this little polypeptide chain. Now this has 3 amino acids, so it is a polypeptide. It's also called a peptide. Specifically, it is a tripeptide. All right, and you see the different R groups? All right, so number 1 is our primary focus in chapter 16. There are secondary structures, tertiary structures, and quaternary structures. So let's go over a little bit of them now. Number 2, secondary structure. This is defined as the regular and repeating spatial organization of neighboring segments of protein chains. So if I have a long amino acid primary structure, just a bunch of amino acids strung together, and if I were to coil it, okay, like a spring, like an alpha helix, the way it coils is referred to as that particular primary structure's secondary structure, referred to as alpha helix. If I had a long string of amino acids, primary structure, just a bunch of little AAs, amino acids linked together. If I were to instead make it go like a zigzag pattern, well, it's almost like it's like an accordion. This would be called a beta sheet, or a beta-pleated sheet. These are the 2 primary structures I want you to be aware of. Alpha helix is like a single protein chain coiled in a spiral with a clockwise twist. And a beta sheet, or as your book refers to it, a beta-pleated sheet, this is where a portion of chains are held in place such that they form kind of like an accordion look. Okay? So those are the 2 secondary structures. Tertiary structure is defined as, and we'll let some of the notes get put down here. It says tertiary structure, this is number 3. So we had primary structure, secondary structure. This is tertiary structure. This is the overall 3-dimensional shape of a protein molecule. 1 protein molecule, remember, produced by regions of secondary structure. So it's kind of bigger than the space this little camera is allowing me here. But if I had an enormously long protein chain, right, you can imagine some parts of the chain would be coiled, some of it would be pleated, some of it will coil. We may have a button hook. Okay, that's when it makes a turn. And then we have there's other types of secondary structures as well. But over time, the alpha helix could stop and turn into a beta-pleated sheet. And then there's other secondary structures as well. But if you take that whole conglomerate as a whole, that's referred to as that particular 1 protein's tertiary structure. Okay? So it's the overall bending and folding of the protein, single protein chain. Number 4, quaternary structure. This is essentially a tertiary structure of 2 individual proteins conglomerated together. Okay, then you take that overall aggregate and go, oh, well, that's the quaternary structure. So the definition for that is the overall 3-dimensional shape when 2 or more proteins are involved and aggregated or grouped together. All right, so that is protein structure and function. Primary structure is the most important of those 4. Okay, so the next topic is all about proteins. So it's all about chapter 16, but it's referred to enzymes. Definition of enzymes: these are proteins that act as catalysts for biological reactions. And if you remember, in general chemistry, catalysts are something that they enter the reaction and speed up the process, but then you kick them out. They are regenerated as products, and they can circle back and they can catalyze more of the reaction. So all enzymes have what's known as an active site. That's kind of like the hotspot or the epicenter of what's going to happen. All enzymes have an active site, and that's where the substrate molecule binds. The substrate molecule, we give it the symbol S, capital S, but it's really the reactant. Okay? We want the substrate to come into the active site, somehow get manipulated, tweaked, or undergo a reaction, and then get spat out of the enzyme as something else, as a product. So it's like you have an enzyme, substrate binds to the enzyme's active site. Reactions take place when they're bound as an ES complex or an enzyme substrate complex. You can either put quotes around that, some people put brackets around that, because that's an intermediate situation where the enzyme is in contact with the substrate bound to the active site. So it will do its work, do its reactions, okay, catalyze certain reactions, and then when a product is formed, it will release that product, which used to be the substrate. It'll release it from the enzyme substrate complex's active site, right? And I'll draw an equation for how that works at the very end. Now, the active site and the substrate, you can inhibit the way in which these guys perform. So sometimes an enzymatic process is inhibited, in other words, prevented or blocked by what's obviously known as an inhibitor. And there are two types of inhibitors that we're going to discuss in this course. The first one is called a competitive inhibitor. That's going to be something that, quote, competes for the active site, right? And effectively shielding the substrate from binding. And another one is the non-competitive inhibitor, which we'll talk about second. So, competitive inhibitor, you see that my enzyme looks the same. Haven't changed anything with the enzyme, but I've got this other kind of black colored reactant that is crowding out the substrate from the active site. So if the substrate is unable to bind to the active site because the beach is too crowded and there's someone else already in his spot, so if he can't enter the enzyme active site, he's not going to be able to undergo the enzyme catalyzed reactions that convert substrate to product. This is called competitive inhibition. This is a competitive inhibitor. Okay? So if my substrate looks like a pizza slice, I've tried to make that competitive inhibitor there sort of look like a pizza slice. It kind of looks like an obtuse triangle though. All right, number two, non-competitive inhibitor. A non-competitive inhibitor is a molecule that, when it binds to an enzyme, the act of it binding to an enzyme somewhere other than the active site, by the way, changes the shape of the active site, making it impossible for the substrate to bind to what is no longer the original looking active site. What the heck do I mean by that? Let me show you. As an example, I have a little circle here, okay, and that circle has a line through it, kind of like a red circle with a line through it. That is my non-competitive inhibitor. You can see it looks nothing like the substrate, right? It looks nothing like the pizza slice, and it's going to attach at the enzyme away from the active site. So you see that little opening on the enzyme I've drawn? That's kind of like the non-competitive inhibitor. When he binds to that little gap right there, that is going to make the little Pac-Man mouth, the little active site, is going to look different. And if it looks different, and if it no longer looks like it can fit a pizza slice perfectly, well, the substrate won't bind. So that's an example of non-competitive inhibition. All right, so I'm drawing it now. Here we have the non-competitive inhibitor bound to the enzyme, and look, the enzyme active site looks totally different. It's much more wide open. It's like Pac-Man opening his mouth really, really wide. You see how the substrate no longer fits properly? So that's non-competitive inhibitor preventing a substrate from binding to the enzyme's active site. And if I can't have an enzyme substrate together in an enzyme substrate complex, I'm not going to be able to undergo the enzyme catalyzed reactions that will change, literally change the substrate into something else, into a product. All right? So let's just put down in the notes what I've just said out loud. When non-competitive inhibitor binds to the enzyme away from the active site, it tweaks the enzyme's active site, and the substrate can no longer bind. All right? If the substrate can't bind, it won't be able to get converted to product. In other words, it's not going to be able to convert to product because it will never be able to bind to the enzyme's active site, forming that enzyme substrate complex. Now, down here, I am just going to draw you a general equation for what all this verbiage means, okay? Basically, we have E, the enzyme, plus S, the substrate. And the substrate is basically like your reactant. And we have a reversible connection between enzyme and substrate, and that's when the substrate is bound to the active site. And then the reactions occur, and then we move on and we form product. Guess what? The enzyme can now swing back to the beginning and catalyze more substrate to product reactions.